Have you ever just stopped and thought about how your computer does, well, everything all at once? It really does feel like magic, doesn't it? But behind the scenes, there's this brilliant system that's directing all the traffic. Today, we're going to pull back the curtain on one of the internet's biggest secrets. I mean, really, think about it for a second. You've got all this stuff happening, your colleague's face on a video call, the article you're reading, that important email downloading, and it's all flowing through the exact same pipe, your internet connection. So how does your computer know what's what? How does your video call not end up scrambled in your email inbox? Okay, so getting the data to the right machine is the first part of the puzzle. That's called host-to-host delivery, and it's handled by the lower layers of the internet. But honestly, that's only half the battle. The real magic, the real challenge, is what happens inside your computer. Getting that data from the machine to the specific app that actually needs it. We call that process to process. And that right there is where our hero comes in. This whole incredibly complex sorting problem is solved by one single, absolutely crucial part of the internet's architecture, the transport layer. Its job sounds simple, but it is so vital. The transport layer basically takes the baton from the network layer. It builds a bridge not just between computers, but between the actual applications running on them. It's the final critical step that makes sure your Zoom data goes to Zoom and nowhere else. So how does it pull this off? Well, it's a really clever two-part addressing system. First up, every chunk of data has an IP address. You've heard of that. Think of it like the street address on a letter. It gets the mail to the right building, in this case, your computer. But, once the letter gets to the big apartment building, it still needs an apartment number, right? That's the port number. It's a number tucked inside the transport layer's info that tells the computer exactly which application, which apartment should get this piece of data. And this brilliant combo, the IP address plus the port number, has a name, a socket address. Now, the transport layer isn't just one thing. It's got two main ways of getting the job done. First up is the super careful, super reliable option. If the internet had a postal service, this would be its certified mail, with tracking and a signature required. It's called TCP. The whole deal with TCP is that it makes a promise. It absolutely guarantees that every single piece of your data will show up, that'll be in the right order, and that it won't have any errors. And it does this by establishing a formal connection before it sends anything. Before even one bit of data gets sent, TCP does this little dance called the three-way handshake. It's basically your computer saying, "Hey server, you there? I'd like to talk." The server replies, "Yep, I'm here and I'm ready to talk too." And your computer finishes with, "Awesome, connection established." Only then does the real data start to flow. So how does it keep that promise of reliability? Well, it's got a whole toolkit. It puts a number on every single packet so they can be put back together in the right order. It makes the receiver send back little confirmation messages called ACKs for everything it gets. It uses something called a checksum to spot any corrupted data. And it even manages the speed, so a fast server doesn't just flood your device with more data than it can handle. And you can literally see that reliability right here. This is the header on a TCP packet. Just look at all that information. All of these extra fields are what let TCP keep its promise. But as you can probably guess, all this extra work, all this extra information, it has a price. Right, and that price is speed. And this brings us to the fundamental trade-off, right at the heart of the transport layer. On one side, you've got TCP. It's reliable, it's thorough, but it's a little bit slower because of all its checks and balances. And on the other side, well, you have something very different. Let's meet our second protocol, UDP, the User Datagram Protocol. And if TCP is that certified letter, UDP is basically a postcard. You just scribble a quick message, drop it in the mail, and kinda hope for the best. This quote really says it all, doesn't it? UDP is brutally efficient. It's connectionless. It doesn't waste time with a handshake. It's unreliable. It doesn't guarantee anything. Its only real job is to grab the data from the lower layer and slap on the port number so it can get to the right app. And that's pretty much it. Its entire philosophy is simple. Just send it. No connection, no acknowledgements, no resending anything that gets lost. It just fires data at the destination as fast as it possibly can. If the network gets busy, it doesn't care. It just keeps going. If a packet gets dropped along the way, oh well, it's gone. And wow, this just shows you everything you need to know. Compare this UDP header to that complicated TCP one we saw earlier. It's tiny, it's just 8 bytes. It only has the absolute bare essentials. This thing is built for one thing, and one thing only: pure, unadulterated speed. So we have two completely different tools in our toolbox. One is careful and reliable. The other is fast and, let's be honest, a little reckless. So how on earth does the internet use both of these to create the seamless experience we all take for granted? Which leads us to the most obvious question, right? After hearing about everything UDP can't do, you have to be thinking, why would anyone ever choose this? Why trade that guarantee of delivery for, well, for what exactly? Well, the answer is all about the application. See, when you're browsing a website or sending an email, you need every single byte to get there perfectly. You can't have a web page with missing words. That's a job for TCP. But what about a live video call or an online game? In those cases, speed is everything. A single missing frame of video that you don't even notice is way, way better than your entire call freezing for a second while it waits to re-download a lost packet. And that is where UDP is king. And that's really the beautiful, elegant design at the heart of all this. The internet isn't built on one single perfect protocol. It's built on a smart choice, a trade-off that's made millions of times a second between the absolute reliability of TCP and the raw, blistering speed of UDP. But what if that trade-off is starting to get old? New protocols are always being worked on. There's one called SCTP, for example, that tries to give you the best of both worlds, the rock-solid reliability of TCP, but without some of the things that slow it down. The choice might not be so black and white for much longer. Which leaves us with one last big question. As we push the internet harder and harder with things like 5G, the metaverse, and real-time AI, what are we going to prioritize? Will the future be built on that old foundation of reliability or on pure speed? Or will it demand something completely new, a totally different balance of both? The entire next evolution of the internet really depends on that answer.